Okay, so we are doing, I don't know what lecture it is, but it's, so we are doing time varying systems, right? Time varying systems, and it is, date is 02/10/2020. Okay, so time varying systems of this sort, x dot equals to f of tx. This is what we will do, right? Where f is defined over 0 to infinity. That's your time interval. X is defined over domain D, Rn. So some assumptions. It's piecewise continuous, locally ellipses, and your origin is a part of the domain, because so that we can study properties of. So let's say x bar is an equilibrium point. Equilibrium point, so f of, that means f of, sorry, t comma x bar equals to 0, right? For all t greater than equal to 0. So that's an equilibrium point definition. So let's develop why is there a need of time varying system, right? Like, so one of the most important problems that we do in controls is tracking problem, right? We're trying to track some trajectories, time varying trajectories and other stuff. So when you are formulating those problems, most of the time they end up in a time varying scenario. So let's just pose one problem. So let's say we have this. So let's say tracking problem. That's so we have, let's say, y dot equals to g of y, some nonlinear function, right? State is y, and suppose that we would like to track a trajectory, right? What is the, and that trajectory is given by some, say, y of dt, a desired trajectory, right? I'm using in terms of y because most of the time we are tracking outputs. So y is generally, for example, if you remember your differential flatness, it was the output that we were trying to track. And y is your position and velocity. So let's say we want to, this is the desired trajectory, right? Yd of t. So for trajectory to be, so some things, like, first of all, when we say we want to track a trajectory, what does that mean? Means your vehicle, means when we apply the control, the solution of this y of t, means the yd of t should lie in that space, right? Otherwise, for it to be feasible, y of d2 should be one of the solutions of this, right? Or in fact, unique solution if we apply the same control. A solution should exist. Then if yd of t is not a solution of that y dot of gy, then I cannot track the trajectory, because the solution that y dot of gy we are solving, it won't be able to give me that. So that means what? So that means y dot dt, if I just differentiate it, it should be equal to g of y dt. And this is also a way, this is very important, like some students don't get it, but if I say that, can you verify if this trajectory is a solution or the above solution? How do you verify? You take a differentiation, right? That's y dot. And you substitute this into this, so both sides should be same, right? That's
homework problem.
Yeah, I think there was one of the input problem here or in the model control.
One of them.
Model control, yes. So that's how you verify that if this is the trajectory of a particular given system. Plug it in this, and when you actually differentiate it, both should be equal. So, so let we define x to be y minus y desired, and you see we always reformulate the problem so that the trajectory becomes the equilibrium point, or kind of. So we always say, because if x is y minus y desired, that means x equals to 0 means what? Y equals to y desired, right? So what is x dot then? Y dot minus y dot desired. So that is g of y minus y dot desired, right? So then we can, so this thing here, basically if you see, if you have to put this into this form, is this can be said at f of tx. The time comes because of this. Even if your actual system, see where did we start? Our actual system was y equals to gy, right? That was not a function of time. But the transformed system, when you change x equals, you choose your x equals to y minus y desired, which is a function of time. Now if you end up in a time varying system. So all the tracking problems mostly will be time varying systems. So that's why there is a need. I'm just thinking, even if you say that, hey, our original system is not time varying, you will end up in a time varying system. So and that's because this is purely function. This y can be written as from here. What is y? Y equals to x plus y desired, right? X plus y desired, and then you have minus y dot dt. So, which is f of tx. Okay, and you can see that f of t0 is 0. See, right? If I say f of t0 means what? Means I'm putting x equals to 0, right? So is that
just means you're starting at the known point, like your initialization point is on the known trajectory.
Yeah, so
You're assuming full known
yeah, this is 0, right?
right?
Because if
Yeah.
when you put x equals to 0, it is z y of d minus y dot dt, right? Y dt, and if you see, they are from here, this equation, this minus this equals to 0, right? Yeah, I just wanted to say that this is the x equals to 0 is the equilibrium point of this equation.
And that just means that you're right on, like there's no error, right? Yeah.
Even at time t equals 0.
Right.
Yes. Yep.
Yeah, I just interpreted at initialization, well, I guess that would be time equals 0, but that means, okay.
So that so basically x is the valid equilibrium point of that new system. So that's good. So that's kind of the motivation why even if your actual system is not time varying, trajectory tracking problems will come time varying problems, and most of our job will be something like, we don't always just go to like inverted pendulum, just go to a stationary point. In case of UAVs or anything, you are tracking some time varying stuff. Okay, so now we come back to quick definitions of stability, like how stability definition applies to time varying systems, kind of. So that is x equals to 0 is a stable equilibrium point of x dot equals to, so from now on our systems will be t comma x, and x equals to 0 is the equivalent point, right? If for each epsilon greater than 0 and any t0, so see now in time varying systems this is appearing because when you start also affects the system, right? So there exists a delta which is not just only function of epsilon but also t0 for all such that your x of t0 less than equal to delta me implies x of t is less than epsilon for all t greater than equal to t0. See, so that's the new definition of stability, where I'm just saying that when you start also matters that so because this epsilon will not only be function. So let's say I start within x0 boundary, right? Let's say within a delta neighborhood of x0, and when you start, the epsilon will be governed by that. So epsilon will not only be function of delta but also t0. It's the boundary where your solution can wander. So if I let's say you're starting, so delta is let's say same, right? So I'm saying that x0 is within this delta, right? This delta boundary. Then there is an epsilon boundary. So if I fix delta, but I'd say I'd start at 2 seconds or 3 seconds, this epsilon will change. So maybe you have a band where like within when you start from time, your trajectory kind of can wander. So the epsilon, the ultimate bound, will depend on the initial time that you started for a time varying system. We want to get rid of it. We want to give a general. So if I can give this uppermost boundary, that doesn't matter when you started and where you started. This is the epsilon, right? So then it becomes uniform. That's the goal. We want to go towards that definition because this is crazy. Like when you start, you should make it independent. Whenever we start, we should be able to say it's t equals to 0, right? So that's the objective, that we want to give definitions which are more independent of t0. So the epsilon is a function in this case of both your delta and t0. So what was the boundary for your x0? How far you are from the origin? And when you started, your affects the ultimate boundary of stability. If that is the case, then the system is called stable. Okay? But there is something called uniform stability now, if you see. And uniform stability is like our previous definitions, where if we can make it independent of t0, then so this new term will be added to all stability definitions. Is it uniformly asymptotically stable? Is it uniformly stable? So that means we are saying doesn't matter. We are kind of getting rid of the time initial when it's saying that it doesn't matter when you started. If you are within this boundary, this is the epsilon. So if we can give an epsilon which is independent of t0 is so that is x of 0 is uniformly stable. Okay, uniformly stable for delta equals to delta epsilon greater than is independent of t0. So basically your delta is independent of. So let's say I fix a boundary epsilon, right? Let's say this is the origin, and I'm saying that for this I can say that if you start within this delta, then you will never, the trajectory will never go out of d epsilon. Doesn't matter when you start. So this is, you get rid of t0. So we will have to impose extra constraints on our stability to guarantee this kind of stuff. Okay, so asymptotically stable, if it is stable and basically there exists a c which is a function of time 0, t0 greater than 0, such that x of t0 is less than c for all time. So every time, if you keep applying this condition, that implies, basically means that x of t goes to 0. Because every time you can choose a new boundary as x changes. And that it has to be less than c, it has to be less than c, it has to be less than c. If you keep repeating this, that means basically x of t goes to 0. But it's a function. It's a function of t0 time. Right, and then uniformly asymptotically stable. So one is UAS, right? Uniformly. The basic idea is all the definitions independent of t0 means uniform. That's all. Like you have to take the message that it is uniformly asymptotically stable. Okay, so that case when so basically there exists a c which is independent of t0, right? You can say that x of t basically goes to x of t goes to 0 in finite time, which is not a function of your t0, and globally uniformly asymptotically stable, gas, whatever. So you're adding uniform again to the global means doesn't matter where you start and when you start, big, like in the whole space you will. So from anywhere. So delta can be basically anything as big as possible. Delta can be chosen arbitrarily, and so is the epsilon, right? So you can. So that's global asymptotic stability. So definitions are simple. What you need to just keep in mind is we want to do an analysis and prove that system is uniformly asymptotically stable or system is uniformly stable. Means basically it doesn't matter where you start. Otherwise things will be crazy and the definitions will be very hard to. So we want to get rid of that T0 independence. So all the definitions that we give, all the analysis we do, Lyapunov analysis will have to guarantee uniform asymptotic stability or uniform stability. Okay. So to do that, we need some additional mathematical. So you remember our Lyapunov candidate function, right? V of x. It was a positive definite function, and so all the nice. It was also not time, but here in time varying systems, you might have a time varying Lyapunov candidate function as well. Also, right? So we'll see how that will be taken care of. Okay, so some new functions. So this uniform stability concepts require us a study of some special, like you have positive definite, right, functions. It's a special class of functions, right? Similarly, there are some more functions that will be needed to treat the time varying systems. Okay, so requires a first. So something is called class K, class K and class KL. So So books uses the fancy K mathematical notation, this kind of L, KL. So K and KL functions, class K and class KL functions. Two type of functions are required. So it basically, one is the one takes care of the positive definite aspects, and one takes care of the negative definite aspects. So the K function will take care of type K or class K functions will take care of the positive definite aspect, that energy is always positive except at the origin, and the function is always going towards 0, right? Or the rate is negative. So let's see definition, right? So we want treating these class K and class KL functions. Definition: a continuous function alpha 0 to a 0 to infinity belongs to class K if it is increasing and alpha 0 equals to 0. So you see any function which, if you increase the inner thing, right? If you increase the, let's say, x squared, it's of course, so if x square is there, if you increase x, it increases, right? It always increases if you increase x. And if x is 0, it is 0. So functions like this. So instead of saying it's always positive, we are saying it's increasing function. Okay, it's increasing belongs to, and this is the boundary where like this is the domain of x. We are saying x is between 0 to a. Okay, which spits out answer from 0 to infinity. So this, the way which I say this means it. This is the what the function x takes, the range of x, and then this is the range of alpha itself. So after you plug in the value, right? So this is,
so 0 to a is the range of x, and 0 to infinity you said is the range of alpha?
of x squared, yes. Okay.
Gotcha, okay.
Okay. So this is K, and there is another thing, like you can call it, like if you remember our radially unboundedness, right? So there is a K infinity function you can quantify when you say alpha of r is infinity as r is infinity. In some functions it might not happen that even if a is not infinity, it might go to infinity. So they are called K infinity function. They will be useful for global uniform asymptotic stability, whereas class K will be used just for stability, asymptotic stability, uniform asymptotic. So basically, you can create a comparison between positive definite and then radially unbounded with K and K infinity. Okay, so both conditions are there. So basically, x square is a K infinity functions, class K infinity. Just to differentiate between that category, whether we can say if a system is globally uniformly asymptotically stable or. Okay. So we will take examples. Don't worry about saying. So if we draw some pictures here, right? So a class K function can be, let's say, 0 to a. So this kind of always. So something like that. So this is R. So basically we are finding alpha of R. It's increasing does not mean that, so this is also even qualify as a class K function. A goes to infinity. So this kind of maximize it. Increasing means it does not decrease. It does not always have to, like one is monotonically increasing, means as soon as you increase x, it increases, but this will also qualify as an increasing function where there's no difference between the previous value and this value. But this is not class K infinity if it stables now, right? Because if A goes to infinity, it just saturates at 1. Then it is class K, but not class K infinity. Okay? But something like this will be like we're just keep going, right? So when a r infinity means that this will also go to infinity, but that will be class K infinity functions. Most of the time won't be useful because you might be dealing with some domains, so class K function should be enough, but when it is about global asymptotically stability, then you will have to use global uniform asymptotic stability. Okay? So some examples will be, for example, alpha r equals to, see, I'm using r instead of x just to differentiate the between. So let's say r to the power c. What is this function? Is it a class K infinity, or you cannot say? What is that?
Depends on the sign of C.
No, sine of c, let's say c is greater than 0.
It's probably always increasing, so it's in K infinity.
Yeah, there's K infinity, right? So because it is at r equals to 0, it is 0. And it's always increasing. In fact, when r is infinity, it is infinity. So, yes. Okay. What about alpha r equals to 10 inverse r? How about that? So this seems to be, I don't know what, if you remember, if you see the 10 inverse r is something like this, right? It kind of at 9 plus minus 9t. After that, kind of saturates,
It's
right?
always increasing, but
Yeah.
saturates, yeah.
So it is
K, but not K
class K.
infinity.
So it's class K. At r equals to 0, it is 0. And so yeah, it's class K functions. Things like that, right? So, okay. So next interesting is, let's go to KL thing, right? Class KL. Class KL. So that is, a definition will be,
K and L, are they designated for any, what does that mean?
they just made like, yeah.
Okay, there's no way to remember, like, it doesn't actually mean anything?
Class K, and yeah, you have to
Okay,
just, yeah,
alright.
it's just a terminology.
Okay.
Like positive definite, they could have said, so this, with positive definite, they're saying K and then KL.
Okay.
Yeah, that's a good question, why is this naming convention was done, and we should find out, but, no. So a continuous function, so this is interesting, you'll see, a continuous function beta, so we will denote, so we were denoting class K functions by alpha, we will denote class KL function by beta. Okay, so that beta takes from 0 to a, from 0 to infinity. So it has two arguments. Beta is it's a function of two variables, x and y, or and answer is between 0 to infinity. Belongs to class KL if for each fixed, so beta is something like this, beta is r and s, it's a function of two variables, r and s, and I'll show you in one moment, you will realize why it is there. But KL, if for each fixed s, let's say I fix x, right, let's say I say s is constant, I'm not changing it, I just choose one s, right? If for each s, beta rs is class K, right? What does that mean? So if I fix s, and if you change r, it's an increasing function, or it will satisfy all the properties of class K function. Okay? Okay, and for each r, beta rs is decreasing function. Decreasing, that means beta rs goes to 0 as s goes to infinity. Okay, so if you fix your r and you increase your s, so s can be time kind of thing, right? So basically you're saying, and r can be like initial condition. So an example will be something like x of t equals to x0 into e to the power minus 2t. So t is s. So if you fix t and increase x0, it increases, right? At x0 equals to 0, it is 0. So solutions of linear time systems, if you see what is the system, like if your eigenvalues are negative, so you get something like this, right? x0 into e to the power at, if you remember. So if the eigenvalues are negative, then it's a class KL function that with time, as the time goes, it decreases. x0 can govern where it started. Got it? So it's okay. So examples will be, as I said, beta rs can be r e to the power minus s. In fact, so if you fix s, right, it's a class k function. If you fix r, it's a decreasing function, so it's a class KL. So both, it has different properties with respect to each variable. With time, my thing should go to 0, and with increasing initial conditions of s, r, it should increase. Beta rs should be r over 1 ks r plus 1. In fact, this is also a KL function, right? If you fix s, increase r, it will increase, right? And if you fix r and you increase s, the denominator kind of goes to infinity and this becomes 0. So it's a functions like this. Got it, guys? I know it's kind of dry.
So the lower limit is 0 and higher limit is infinity.
Yeah.
And it's never negative r and s.
Okay, let's see some properties of these functions. Some properties, let's say, so it's a lemma, basically lemma 4.2, I believe. So let's say alpha 1, alpha 2 belongs to K, class K, and alpha 3 and alpha 4 belongs to K infinity, and beta belongs to KL. Okay, so there are 5 functions that we are talking about right now. Let's see what their properties are. First property is alpha 1 inverse also belongs to K. That's good news. Is that true?
So it says.
Yeah, alpha 1 inverse also belongs to, and inverse means, you understand what inverse means? So if I have, let's say, what was that, r to the power c, right? Alpha equals to r to the power c. So what will be r in this case? R will be 1 by c of alpha equals to r, right? So that is alpha inverse, right? So I am able to find out the inner, that is alpha inverse, not like in 1 over something. Inverse means functions inverse. I should be able to find the argument. So if I have gx equals to y, then y equals to g inverse, x equals to g inverse y. So that is the inversion, function inversion, not the actual inverse of, right? So you see now, if you increase alpha equals to 0 means r is 0, and when you increase alpha, r also increases. So it is K, class K function. It's okay, so don't confuse alpha inverse with the actual arithmetic inverse. It's the inverse mapping, basically. So I'm saying I know y. In this case, I know y, give me x. So that will be g inverse y. So that will be like, for example, cos theta equals to y. What will be theta? Theta equals to cos inverse y. You got it? So that's the inverse we are talking about here. Function inverse mapping. So that's one property you can verify. We already kind of verified here, but alpha 3 inverse equals to k infinity. So if it is alpha 3 belongs to what? K infinity, right? So if it is a k function, the inverse mapping is also k. If it is k infinity, the inverse mapping is also k infinity. Class k infinity, okay? And then let's say third, alpha 1 of alpha 2. And whatever I'm writing will be used in the proofs and theorems and things like that. So alpha 1 of alpha 2 belongs to class K. Of course, so if it's a function of function, right? So it makes sense. You can easily visualize this proof. Fourth is alpha 3 of alpha 4 is K infinity. That's natural. Okay. Last one, the most important one is this. So sigma rs, I'm defining a new function, which is basically alpha 1, right? Alpha 1 is class K function of beta of alpha 2 r comma s. Let's see that. So what is the class of this function then? So I'm saying first, so it's a function of function, right? So alpha 1 is a function of a class KL function, and class KL is a function of a class K, and so this sigma will also be a class KL function, right? So it will belong to KL. You can easily so this function definitely is class KL, right? And if it is class KL, if it goes to 0 as s goes to 0, alpha 1 of 0 is also 0. So this goes to 0. And if you increase this, then this increases. So the resultant function where function of function means the inner argument is KL function. So then the overall function will be a class KL function. Something like this, for example, I don't know if you want to verify. Let's say x equals to x0 into e to the power minus 2t, right? And let's say alpha is, let's say, x squared. So what will be x squared of this? So x squared is an alpha function, right? But x itself is a KL function, so x square will be nothing but squared of this and minus 4 of this. The resultant function is still a KL function, right? So that's the so let's put the definitions, stability definitions now in terms of class K and KL functions. Now you can see, right? If the solution is KL, then it's a asymptotically stable system, right? Uniformly asymptotically stable. Right? If I can show that my solution x of t is a class KL function, then it is stable, asymptotically stable system. So let's see. Let's give these definitions. Oh Jesus. Lemma, I don't know what lemma is that. From 4. Anyways, whatever lemma is this, we can cook up something. So some lemma. So x of I'm just re-giving you the definitions in terms of class K and KL thing. X of 0 is uniformly stable if x of t is less than equal to alpha of x of t0. See now what I am saying here. Where alpha belongs to class K. So if x of t see, it doesn't matter what your initial condition is, right? T of 0. What is T of 0 your is? It only depends on the size of alpha belongs to class K and x of t0 is less than equals to some C. Okay? So this means there is a bound. I can always find a bound. Of course, that bound is increasing in nature. If you increase your x of t0, how far you start from the origin, the bigger you will be away from the origin. So the bigger that boundary will be. But right, so you can give this definition for uniform. And second, it is uniformly asymptotically stable if your x of t now can be written as beta x of t0 and t minus t0. So this is R, this is S. See? So that means this beta is class KL, right? So what happens when when this is class K with x of t0, right? So if you increase x of t0, overall things increases. But when t minus t0 goes to infinity, then doesn't matter where you started, it goes to infinity and it's uniformly asymptotically stable. Okay? So, and for x of t0 less than equals to C. And it is third is if C can be chosen arbitrarily, doesn't matter how large, arbitrarily, then it is globally uniformly asymptotically stable. Doesn't matter how far I start from the origin, function will be there. And for that, this has to be then,
This might be lemma 4.5.
Oh, this is 4.5?
I think so.
Okay, 4.5. Got it? So, couple more things before we actually dive into how we actually apply this to nonlinear time varying systems. X of 0 is exponentially. See, right now we were only dealing with asymptotic stability. Asymptotic means t goes to infinity, x goes to 0, and t, it's a vague condition. So you're saying that it will someday go to the origin. So that's, but if you're like in linear system, if you're asymptotically stable, you're also exponentially stable, right? Because of those eigenvalues coming in the solution. Exponential means in finite time, you exponentially go fast to 0. So if x of 0 is exponentially stable, if it is uniformly asymptotically stable with beta, if your beta, the KL function is of this form, kr e to the power minus r or some gamma s. So if your KL function finally is of this form, you can say, because now it's exponentially going fast. And linear systems, if you see, x0 e to the power minus 2t or anything, they are all of this form. Okay. Couple more minutes, right? So lemma, I don't know what lemma is this again, but I will state it. Consider the scalar autonomous ODE alpha dot equals to minus alpha y. Yes, I'm saying that if I have an ODE of this sort where y dot equals to negative of a class K function, right? Alpha is a class K function. See, this is class K function and locally Lipschitz also. Okay, locally Lipschitz condition, and it's class K, and y of t0 equals to y0. Then if you can put your ODE, your y dot into this form, then what can you say about the solution? Right? Then locally Lipschitz in 0a, and for all, then we have a unique solution. Then we have a unique solution which is called as y of t is of sigma y of 0 comma t minus t0. So your unique solution will be of this form. If you can show that your ODE, we are always dealing with this x dot equals to something, right? If you can show that your ODE is of this form, where y dot is negative of some class K function, means what? That thing is always positive, and it at 0 it is 0. So then you're good. Then, and it has to be, of course, a function of. So something like anything, any y equals to minus y squared, or y equals to minus y4, or anything like this. You can see the solutions will be always of that class K function. What does that mean? That means y of t is uniformly asymptotically stable, right? This system is uniformly asymptotically system. If you have a solution like KL, then system is uniformly asymptotically stable, right? Because as t minus t0 goes to infinity, this goes to 0. Right? So sigma is a KL type function. Okay, you can take an example to show this. So example will be y dot equals to minus ky. Okay. So where ky is class K function. In fact, it is class K infinity. It's increasing. You increase y. Y goes to infinity. Ky also goes to infinity. Y equals to 0. Ky equals to 0. So this is of that form, right? Y dot equals to minus of alpha of y. Right? Then if you get just, what is this solution? You know what is, right? You can find the solution to this ODE, right? Is y of t equals to y of 0 into e to the power minus kt. Basically, that's the solution. Right? Yes, no? What is it like? This is same, right? X dot equals to ax. So if a is minus k, so e to the power at and minus kt. And so you can see now if I say y of t equals to y of 0 of e to the power minus kt. Right? So this is basically sigma of y0 into t minus t0, right? This can be t minus t0 also. T0. So that means it's class KL, t minus t goes to 0. So all you have to do is, if you are able to show your v dot or Remember, we are always finding this v dot, x dot, and everything. If you can show that it is the differential equation is of this form, where alpha is a class K function or class K infinity, then we're done. It means the solution will be a class KL function, and which means good things, as uniform asymptotic stability, or if it is class K infinity, global uniform asymptotic stability. Okay? Good. Now I think we are ready to give all these awesome theorems for stability of time varying systems in next class on Wednesday. And then Friday, yeah, so as I said, I think by next week we should be able to start. We'll start with sliding mode control. And, but bear with me for one more. I know you guys are having hard times. Eyes are hardly open. But believe me, we'll